Hi, this is Professor Kim Nelson with the Jewelry Design Department at the Fashion Institute of Technology, doing another tutorial in our series of tutorials. This tutorial is going to be in support of drawing three-quarter views. Basically, some ideas or concepts that you need to understand. I am doing this tutorial in Rhino, which, as you guys know, is a 3D CAD program. It's just going to be easier to draw and explain here than it is on a pencil and paper. Besides, I've got no way of recording a pencil and paper and uploading it for you to take a look at. So, first principle I want you to understand is that you work with ellipse templates when you do these. And those ellipse templates are basically a slice of a sphere. So if we're working with a 17 millimeter diameter ring bore, okay, that 17 millimeter ring bore actually represents what's going on in the top and the side view. Let's take this one, for example. Okay. Every three-quarter view has axes, just like we discuss in Rhino. Okay? The axes in the three-quarter view and the side view are clearly visible. The axes in the top view are not. The z-axis. The z-axis in the top view it's coming straight at you. Okay? So in this example, this ellipse, which I just drew willy-nilly in here, in effect rotates this z-axis forward like so. Okay? And the x-axis which is visible in these two views clearly is straight across. The x-axis in this view is coming straight at you. Okay? It's important to take a look at this and be comfortable with what it represents. Okay? Now, this would be a cheating three-quarter view. It's basically just tilting the ring forward. True three-quarter view tilts the ring forward and from side to side. Something more like that. Once we do that, that rotates our z-axis upward, and we have rotated our y-axis as well. I mean our x-axis as well. Sorry. Now our x-axis is moved those of you who have watched me go through this frightening exercise before know that what I am looking for here to establish this x-axis is to find where it intersects the boundaries of this running straight up and down. Because all of the z-action lines run parallel to the z-axis. So that the x-axis has now rotated like so. Okay. This relationship, once again, is important to understand. Our y-axis, the one receding in this direction, is always the short quadrant of the ellipse. Like so. And that's too close to the other color. So here's your x, y, z. Here's how it relates to the top and the front, the top and the side view, and how the top and the side view can feed into a three-quarter view. If you ever have the burning desire to do so, you can actually bring in a side view and a top view and carry the information up and down and draw a technically accurate three-quarter view. I don't recommend it. It's an awful lot of work. But what is important to understand is the relationship. Okay? The more one of these, anytime one of these spins, it affects the others. Okay, so if I twirl this one more to the side, because I want to see more of the side view of the ring, okay, once I do that, then I now have to spin this until it rotates and fits within this boundary. Like so. Okay. Once I've done that, That changes, of course, the y-axis. And the x-axis. Okay, I'm doing this by eye. I'm not being careful. It's a little bit off, but okay, that's fine. X-axis would be more or less that. Okay? And of course, it radically changes what happened over here. If I want to see more of the side, then I can't see as much of the top. That's the principle, that everything is sacrificing something else. Okay, so this is critical to understand. This relationship can't be avoided. So every time you draw an ellipse in here, okay, you are making a statement about what parts of the ring you're seeing. And if you're seeing more of the side, you're seeing less of the top. If you're seeing more of the front, you're seeing less of the top. If you're seeing more of the top, you're seeing less of the front or side. Okay? The wider this ellipse is, the more of the front of the ring you're seeing. So if I make it a fat ellipse, like so, okay? I haven't changed this axis. I haven't changed this axis. Well, this is always vertical. I have, however, changed these two. Okay, so if I have this view set up, the way to get this accurate in Rhino, guys, is I'm just going to mirror it. If I mirror that straight up above, and then do curve, straight line, tangent to two curves, and I do that, I can get the very, very accurate depiction of what it is I'm trying to do. And what you can see is when I do that, that has changed. Which of course means that this has changed. And so on and so on, okay? So you have to pick what you want to see the most of in your ring when you determine what kind of ellipse you're using and how you're arranging it, okay? The more vertical you arrange your ellipse, the less of the top you're going to see. The fatter of an ellipse that you choose, the less of the top you're going to see. Okay, if you have a really fat ellipse, well, you can see a fair amount of the front and a fair amount of the side, but you're not going to see much of the top. Okay, so it becomes, and even then you're going to see less of the side. So the fatter is a front view priority. Vertical is a front and side view priority. Horizontal, the more horizontal this gets, the more of the top view you get. The more horizontal and narrower it is, the ellipse, the even more of the top view you can get. Okay? So with this in mind, and because I'm recording this before class, I'm going to get on to how I actually would use this information. A typical three-quarter view for me is going to put that at about that angle, my ellipse. And I'm going to thin that ellipse up quite a bit. Something about there would be typical for what I would do. Okay? It is, I don't really care anymore about what's going on up here. Doesn't interest me. But I do care about what's happening over here, because that's useful information to me. So I may or may not draw this on my page, but either way I'll be aware of it. Okay. I will be aware of the fact that this represents my ring rotated towards me. And that any extension of this line above or below basically represents my z-axis, my depth extending above and below my ring. I really do need to have my y-axis and x-axis in here to draw accurately, so I will put them in. The y-axis, once again, is just the short axis of the ellipse. X-axis is what would happen if I bring this over. And by hand, you can't get that accurate with this, but you can get quite accurate with the computer. Okay, it's where this ellipse runs into a straight vertical on either side. Okay, so this is basically the information I need to start to draw. I am going to draw a 2mm thick shank with a 12 by 9 pear shape. So I'm going to take the same ellipse template. Your ellipse templates have little dots on them. And I'm going to copy it by sliding it along this axis. Just line up the dots and slide it along. I'll slide it 1 millimeter. And another 1 millimeter in the other direction. And as long as I stay lined up on this slide like a trombone, I'm in good shape. Okay? I'm alright. Now, if I need to put a thickness on this, which I do, okay, then I need to pick the same degree of template. The same degree means width of ellipse. So I'm going to take one that's big enough to give me the front and back of my ring. Okay, we know that for our purposes generally this would be 21 millimeters, 2 millimeters, so a total of 4. So okay. Okay, so now we have this. I am going to bring the exact same oval template, okay, that I used before. But I'm going to make it fit into this new diameter, okay? I'm going to have to do something that's a little confusing. The easiest way to line this up is using the long axis of the ellipse. And using axis, 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 axis is very confusing. These are the axes of your drawing. This one happens to also be an axis of the ellipse. The ellipse has 2 axes. The other axis runs the full length. Okay? And it's useful to draw it because you can see the nice right angle here. The x-axis in your drawing is never, ever, ever equal to the x-axis in your drawing. The only time that those two are equal is when the whole ring is laid out flat horizontal. Okay? Once you leave horizontal, these two have a diverging direction. They don't ever match up. So, but this is useful to me because I can use it to take my center ellipse here and just copy it. Get a bigger template, the size I need. And except for I made the mistake of putting that in the wrong ellipse. Sorry. I should have put that in the middle ellipse. There. Take my center ellipse. Get one the same degree, just a bigger size. Unfortunately, I didn't extend that curve so that it would intersect. Because you would draw this line. You also have dots on your template here and here where these intersect. So I would just use a larger template, line it up on those long poles, those long axes. Like so. Okay. This is going to have the exact same axes as this. In fact, it has the exact same. These ellipses share the exact same axes, which is why I can now use the same drawing axes for this large ellipse because it's based on the same information. I'm going to go ahead and take that big ellipse and copy it, just like I did the inside ellipse, sliding along this narrow axis like a trombone once again, and once again 1 millimeter front and back. Okay, once I've done that, I've drawn my shank. Okay, only thing I have left to do is to take this curve and this angle with my ruler or by freehand and copy it here and here so that I can close off the drawing. And of course Rhino gives me the tools to do it by clicking. And that's what Rhino's here for. And I could erase, if I wanted to, any confusing lines. Okay. So there's a shank sitting in the proper orientation. Notice how it gets thinner here, fatter here, thinner here, fatter here. That's perfect. That's what happens in real life, in perspective, and by using the same template. And if you're in Rhino, guys, and you're doing this on a computer, don't do an offset curve. Scale the original ellipse. If you offset it, you will get a static width here, and that is not accurate in perspective. In perspective, this is always fatter, and the foreshortened part, look how foreshortened this is. Okay? Okay? This is this. Look how much shorter it is, how foreshortened it is. Because it is so foreshortened, you have to keep that in mind. Okay, so this will give you the shank. You can see how the foreshortening is important. This is going to be particularly true as we draw our stone. I told you I was going to draw this for a 12 by 9 pear shape. So I'll draw that over here. Inside of this box. Like so. I'm going to keep the box surrounding it. I'll move this back over into our main drawing area so we can see it. Okay. I'll actually offset this to get a table for it. I'm just going to do it by eye. Like so. And I should be able to offset that box the same way. Oh, nope, the rectangle changes proportion. Good to know. Okay. The thing to remember when you're drawing a stone is that you just need to have a circle. You can decide if you want the circle to be the largest dimension or the smallest dimension. I'm going to go with the largest dimension for this. Okay, so it'll be a 12 millimeter circle. Once I know that, I can draw my stone very effectively over here. This is where keeping the side view information in mind is important. I'm going to extend this curve a little bit so I have more room. Okay. Offhand, I know I need to get off the finger with this about half of its short width, which is 9. I need about 4.5 millimeters. Okay. So if I measure off 4.5 millimeters over here, that's about, I don't know how that ended up being, 8.5. Okay. That's about the height I need to have my stone sitting at in the 3/4 view. Okay. And once again, it's really important to keep in mind how much this is foreshortened. Turn off the grid. This is coming off the outer surface of this ring. Well, over here it'd be from here up. To the girdle of the stone is really not very far. It's this distance right here. Now that I have that elevation, remember, since our z-axis is always a straight line, any circle along the z-axis is like a slice on a pipe, a slice on a cylinder. It is a straight ellipse. Okay? So knowing that, I can make an ellipse up here to represent that circle down there, and it will be simply a horizontal, regular, straight, horizontal ellipse. This is this. Now the question I have to ask myself is, how far out does this go? Okay. Frankly, there are ways to come up with that. I'm running out of time. There are ways to come up with that. One of the most accurate and honestly the truthful way to do it is to take that y-axis, the short diameter of your ring ellipses, carry it up. Okay. You're going to carry a perpendicular straight down from this line. Okay. Let me do what I want to do. There we go. Okay. This is the real dimension here. This is the unforeshortened dimension. So from here, you can actually do a 12 millimeter diameter circle, and where it cuts off should give you maybe not. I haven't done this in a long time where I've tried to actually calculate how to pull this information from the side. I use it mostly just to gain elevations and depth. So that might be true. Let's draw it and see. Seems too long to me. Well, the first challenge I'm facing is that it is not equidistant on both sides. So, no, it won't be terribly useful to us. But it is a lot more round than you would think. That is, I made a mistake in there somewhere. We're not going to worry about it. We don't have time. But yes, a fairly fat ellipse would actually depict this well. And then within this ellipse, using my axis lines at the girdle, I can reconstruct the proportions of my stone. I can measure the distance along here, because this is the true distance, so I can make that a full 9 millimeters. It is not a foreshortened distance. And I can offset this curve, both sides, to intersect, and that would allow me to have a square, or a rectangle I should say, in which to draw my pear shape. Okay. And like I said, we got a little knocked off here a bit, but that's close enough for the purposes of the time I have. I don't have time to backtrack and spot where my CAD inaccuracy might be. That is sufficient to demonstrate the principle, and the principle is that this box represents the same space as this box. And you'll see it's a little squatter. It looks fatter, but it isn't. It's the same width. It's a little squatter. When I carry that information of the pear shape up into there, it'll be properly foreshortened. And you can see it looks like it is sitting where it should sit. Okay? That is a believable ring shank in perspective with the girdle of this size of stone floating in space. Gotta run, because I'm about to see you in class. Thanks for paying attention.